Hello and welcome to the second video about the preparation of Aryl Iodides. This video is about nucleophilic iodinations of aryl halides, sulfonates and other electrophilic arenes, including diazonium salts. As usual, there's a PDF version of the slides under the Posts tab of my channel. Aromatic nucleophilic substitutions at electron-deficient arenes proceed by an addition-elimination mechanism. The addition step implies a loss of aromaticity and is usually the slowest step. The non-aromatic anionic intermediate is stabilized by electron-withdrawing substituents at positions 2 and 4 of the leaving group, and the best leaving groups are fluoride and nitride. Aromatic nucleophilic substitutions can also proceed by an elimination or deprotonation elimination mechanism with an intermediate arene. Here, the order of leaving group ability is reversed, and iodide or bromide are substituted faster than chloride or fluoride. Substitutions can also be catalyzed by transition metals, especially copper, nickel or palladium. The metal first inserts into the carbon leaving group bond, and electrophilic iodination then yields the aryl iodide. Iodide is a good reducing agent, and when diazonium salts are treated with iodide, single electron transfer occurs, without the need of any further catalyst. The resulting aryl radical then reacts to the aryl iodide with the iodine formed by oxidation. Let's check some specific examples. Here, dinitrochlorobenzene, a classical substrate for aromatic nucleophilic substitutions, was treated with a large excess of sodium iodide in hot DMF. The reaction probably proceeded by an addition-elimination mechanism, because only one isomer was formed. 4-terts-butylchlorobenzene is much less reactive than dinitrochlorobenzene, and substitution by iodide can only succeed via arene formation or transition metal catalysis. Here, with 10% of a nickel-0 complex, a slow but regioselective substitution occurred at 120 degrees Celsius. In metal-catalyzed substitutions, aryl bromides react much faster than aryl chlorides. Here, copper oxide and proline as ligand catalyzed the conversion of bromotoluenes into iodotoluenes. 4-bromotoluene gave a higher yield than 2-bromotoluene because of steric crowding in the latter. Even brominated acetanilides do undergo such substitutions. In this case, only bromide was substituted, not fluoride. Instead of copper, also nickel can bring about the substitution of bromide. A higher reaction temperature was, however, required compared to the previous example. 2 halopyridines are similarly reactive as 2 or 4 nitrohalobenzenes, because nitrogen is more electronegative than carbon and better capable of stabilizing a negative charge. It has been found, however, that acids strongly accelerate the substitution at 2 halopyridines. Acid catalysis is, of course, only applicable to nucleophiles that are weak bases. Otherwise, the nucleophile would be protonated and its reactivity greatly diminished. Iodide, fortunately, is a weak base indeed, and acids can therefore catalyze its reaction with 2 halopyridines. The reactivity of the 4 2-halopyridines toward nucleophiles depends a lot on the nucleophile and on the precise conditions. It is therefore difficult to predict correctly if in a given substitution 2-chloro or 2-bromopyridine will be more reactive. In this example, 2-chloropyridine hydrochloride was refluxed with sodium iodide in acetonitrile for 24 hours to yield the expected 2-iodopyridine. By the way, 2 and 4 halopyridines should be better stored as salts, because the free bases sometimes oligomerize by quaternization. Here, 2,6-diiodopyridine was prepared from the dichloride by strong heating with sodium iodide and hydroiodic acid. Phenanthrolenes are more reactive than monocyclic pyridines, and dichlorophenanthroline reacted cleanly with hydroiodic acid already at 100 degrees Celsius without the need of any sodium iodide. These conditions, that is, hydroiodic acid without sodium iodide, did, however, not transform 2-chloropyridine into 2-iodopyridine efficiently. 2-bromopyridines were converted into 2-iodopyridines with a mixture of acetyl chloride and sodium iodide in refluxing acetonitrile, probably via an intermediate N-acetylpyridinium iodide. Alternatively, an excess of potassium iodide with catalytic copper oxide and proline also brought about this transformation, but the reaction proceeded more slowly than in the previous example. 3 halopyridines are much less reactive than 2 or 4 halopyridines. With the aid of a copper diamine complex, 3-bromopyridine was cleanly converted into 3-iodopyridine. Chloropyrazines are slightly more reactive than 2-chloropyridine and also react with iodide faster under acidic than under neutral or alkaline conditions. In this example, the starting compound contained an acid-sensitive hemiaminal group. The halogen exchange was therefore conducted at -50 degrees Celsius with 5 equivalents of trifluoroacetic acid, and the yield was only fair. Under neutral conditions, however, the chloropurine did probably not react at all with iodide. Here the conditions of nucleophilic iodination had to be optimized because reduction and hydrolysis of the starting phosphate competed with the nucleophilic substitution by iodide. With an excess of iodo-trimethylsilane and a small amount of water, the target product was obtained in high yield, along with a bit of a reduced byproduct. Bromo and chlorophenyl groups remained unchanged. One convenient way to prepare Aryl Iodides is from diazonium salts. These can be generated by dehydrogenation of aryl hydrazines or, better still, from anilines and nitrite. Unlike the classical Sandmeyer preparation of aryl chlorides or bromides from anilines, in the case of iodide no copper catalysis is required, because iodide is itself a good single electron donor and reducing agent. An intermediate aryl radical reacts with iodine to the aryl iodide. Recently, the one-pot transformation of aryl hydrazines into aryl iodides has been reported. Here, for instance, this reaction was accomplished with air and 1 equivalent of iodine in DMSO, and the yields were generally high. Aryl hydrazines are, however, made from anilines, and it is therefore usually more convenient to convert an aniline into an aryl iodide directly, without preparation and isolation of a hydrazine. This example is similar to the previous one, the main difference being the catalysis by potassium terzbutoxide. This here is a classical Sandmeyer type iodination of an aniline. A solution of the diazonium chloride was slowly added to a large excess of potassium iodide in water at room temperature. Because the product is insoluble in water, this reaction sometimes foams a lot. Primary or secondary alcohols are unsuitable surfactants or solvents, however, because these will generate reduced byproducts. Tertiary alcohols, acetonitrile or acetone, are more resistant to oxidation and could be helpful to suppress foaming. This example is a newer, optimized version of the previous one. 3 equivalents of potassium iodide were sufficient to attain a high yield. In this example, the diazonium salt was converted into the iodide directly, without isolation. The main problem of such reactions is to find the right proportion of water and organic solvents to achieve a sufficient concentration of all the inorganic and organic reactants. Here the reaction was conducted in methanol, with carbon dioxide as acid, and no extensive reduction to benzene occurred. This is another example of one-pot iododeamination of an aniline in a biphasic reaction mixture. Instead of iodide, diiodomethane was the iodine source in this case. The diazonium salts prepared from 2 or 4 aminopyridines or nitroanilines tend to hydrolyze to hydroxypyridines or nitrophenols. Here the yield of target iodopyridine was only 57%, probably because of partial hydrolysis of the diazonium intermediate. In such instances, it is therefore better to conduct the reaction under anhydrous conditions. In this example, diazotization was achieved with pentyl nitrite and iodo-trimethylsilane. Another way to prepare iodoarenes is by iodination of arenes, as in this example. Depending on the substituents, the reaction of the arene with iodine can proceed by an anionic or cationic intermediate, or be an almost concerted addition. So, what can go wrong? Iodide is the most nucleophilic halide and also a good reducing agent. Here, for instance, instead of displacing a diazonium group, hydrogen iodide reduced it to a hydrazine. Telesubstitution then gave a low yield of an amino iodopyrazine. Here, a dibromo-nitroimidazole mainly yielded a reduced product when heated with an excess of potassium iodide and sodium sulfide in acetic acid. Typical byproducts of metal-catalyzed halogen exchange reactions are biaryls. Depending on the conditions, these may even become the main product. In Sandmeyer reactions, other nucleophiles can compete with iodide and yield byproducts. In this example, one of the intermediates reacted with the solvent acetonitrile to an acetanilide in a Ritter-type reaction. With tertsbutanol as solvent, a higher yield of aryl iodide was achieved. Here are some more examples that you can also find in the description of this video. On my channel there is also a playlist about the preparation of aryl bromides, which you may find interesting. Thanks for watching and see you next time.